I had everything ready to show a beautiful picture of my cat, and he started licking his butt. Anyway, we're going to talk about derivatives today. And we're going back to that same concept that we've been, this is probably mildly distracting. We're going back to the same concept that we've been introducing this whole class, which it's only the third section, but okay. It's the idea of secant lines and tangent lines. And the whole idea that, oh, I should pull up this link for myself, which is not accessible there. It's the whole idea that that if you have a secant line and your secant line has 2 points getting really close together, well, that is a tangent line, right? We saw that with this little picture. Get the 2 points closer together, it gets closer and closer to the tangent line, closer and closer to the tangent line. As they get really, really, really close together, we basically are at the tangent line. Okay? What does really, really, really close together mean? That's a limit. Okay? And that's what we're doing today. Okay? So let's look at this function. Don't worry about the graph yet. There's a lot of stuff going on in the graph. Don't worry about that. Let's just look at the function x squared. All right, that parabola looks like this. So I want you to find the slope of the secant line. We've already done this before. Find the slope of the secant line between the points where x equals 2 and where x equals 2 plus h. So we know what the slope is, right? We know that the slope of the secant line, all right, that's just going to be the change in y. So f of the second point minus f of the first point divided by the change in x, right? It's just rise over run. Well, the first point, x is 2. Oh, first point is going to go over here. X is 2. What's the second point? X is 2 plus some small little increment. And we can see that another way with the graph, okay? We're looking at this secant line, right? The secant line between those 2 points. And here is x equals 2. And here is x equal 2 plus some small number h. So h is just the distance, the horizontal distance between those 2 points. All right. And notice that if h gets really, really small, the secant line will get really close to a tangent line. So now we just plug things in. What is the function value when we're input 2 plus h? The function is a rule, and that rule tells us to square our input. So we're squaring our input. And squaring our input looks like this. The denominator is much, much nicer, right? We have a plus 2 and a minus 2. The denominator is just h. So when we look at this graph, right, this distance over here is just, it's rise over run, right? That's our rise. It's the distance between the output of one and the output of the other. All right, and we just go simplify. All right, so we square that and we get 4 plus 4h plus h squared. You could FOIL that all out to see where that comes from. 2 squared is 4. And again, we get some really nice cancellation here. We have a plus 4 and a minus 4. They cancel. And this is just 4h plus h squared over h. Now we really want to cancel, but you can't cancel in rational functions unless everything's factored. We have to fully factor it. Factor out an h on the top, and we're left with 4 plus h. The bottom's alone. Now they have the same factor. There's a factor of h on the top, factor of h on the bottom, and we get beautiful cancellation. It's not super important that you can do this. In a typical calculus class for people who are going into like STEM and math and stuff like that, that's an important skill. For our class, it's not super important, but it does show you something. We're curious about the slope of the secant line between when x is 2, which is at this point 2 comma 4, and at 2 plus some really, really small number. And I said, we found the slope of a secant line between x equals 2 and a really small increment up. So what happens as these 2 points get really close together? As these 2 points get really close together, h is getting really, really small, right? H is just the distance between these 2 points. So what we've done is we found the distance for any h. We found the slope for any distance h. And as h gets really, really small, what happens to 4 plus h? As h goes to 0, the limit as h goes to 0 is going to be 4. This is a linear function. We know linear functions are continuous. And if something's continuous, the limit is equal to the function value. So the limit as h goes to 0 is just when h is 0. And that's what we have somewhere in letter B. Make these 2 points infinitely close together. This is basically what I was saying. Okay, the 2 points are infinitely close together as h approaches 0. As that distance between them, h is just the distance between the 2 points. Well, the distance between the inputs, technically. So what we're going to want is the limit as h goes to 0 of that slope. But again, this is a linear function. So it's continuous. So the limit equals the function value. So we can just plug in 0. And you've now done your first derivative. We'll formally introduce what the heck a derivative is, but it's just the slope of the tangent line. Okay? And the tangent line is just what happens when the secant line gets really, really small or really close together. The points in the secant line get really close together. That's a tangent line. That's a derivative. We got a bunch of derivatives definitions coming up for you. 50, don't worry, it's not actually 50. That's an exaggeration. But we have a lot of definitions coming up for you to talk finally about what the heck a derivative actually is. But we've done it. The slope of the tangent line was 4. That was our very first derivative. Congrats.